This video will be going over section 6.2, which is the sum and difference formulas. So what we mean by sum and difference formulas? Well, we need something that can address a question like this. Suppose we have sine of 60 plus 60. Does that equal sine of 60 plus sine of 60? Well, let's check it out. So on the left side, 60 plus 60, that would be the same as sine of 120 degrees. And what is sine of 120 degrees? That's going to be root 3 over 2. Now sine of 60 is also root 3 over 2 plus root 3 over 2. So what we get is 2 times root 3 over 2, or just root 3. So what we see is that these are definitely not equal to each other. So the point is, if we have something like this, I mean, we did 60 plus 60, but if we have something like this, 45 plus 60, well, that does not just equal sine of 45 plus sine of 60. Now, it would be nice if it did equal that, because 45 and 60 are both on the unit circle. But on the left, sine of 105 is not on the unit circle. So we need a strategy to be able to solve something like this when we have an angle that is not on the unit circle. And that's where the sum and difference formulas come into play. So we'll talk about the sum and difference of cosine and sine first. So for cosine, if we have the sum of two angles, A plus B, or A minus B, how we go about evaluating this is we say cosine of the first angle times cosine of the second angle, and then we change the operation. So if we're adding A plus B in the original, we're going to subtract. If we subtract in the original, we're going to add. And then we have sine of A times sine of B. Alright, so this is an identity. This is the sum of cosine. I guess sum or difference of cosine. And then for sine, how sine works is we say sine of the first, cosine of the second. Now for sine, we keep the operator the same. So if we add originally, we keep this as an addition. And then similarly, if we subtract, we keep this as a difference. And then sine of B times cosine of A. So this is the sum or difference of sine. All right, so these are the sum and difference formulas, or sum and difference identities for sine and cosine. So let's look at an example and see how this works. So this question says, find the exact value of sine of 165 degrees. Well, the problem here is that 165 is not a value on the unit circle. So what we want to do is break 165 down into two angles that when added together they equal 165. Now there are many different options we could choose. I'll list a couple of these. We could use 120 degrees plus 45. Those are both on the unit circle. What else? We could say 60, 30, 135 plus 30 degrees. Those are probably the two obvious ones. So we could use both of those. We could also write this as a difference. So we could say 210 degrees minus 45. That would be possible, and then we could keep going. So it doesn't matter which pair we choose. I'll just select this first pair. So what we're going to do is we're going to say sine of 165 degrees. I'm going to rewrite that as sine of 120 plus 45. Okay? And then using the sum formula that we just saw, we're going to say, I'll write this like this, 120 plus 45. So we're going to say sine of the first angle times cosine of the second angle. For sine, we keep the operator the same. And then it's sine of the second angle times cosine of the first angle. And then from here we just evaluate and simplify. So sine of 120, that's going to be positive root 3 over 2. Cosine of 45 is root 2 over 2. I multiply those two together. Add that to sine of 45, which is root 2 over 2. Cosine of 120 is 1/2. All right, so from here, these first two, what we say, we multiply the top together, multiply the bottoms together. Root 3 times root 2 is root 6. 2 times 2 is 4, plus root 2 times 1 is root 2 over 4. I have a common denominator. We can write it like this. Don't add the root 6 plus root 2 and make that root 8. That is not correct. So what we'd say is that sine of 165 degrees is equal to root 6 plus root 2 divided by 4. And you can check this on your calculator. If you punch in sine of 165 degrees, make sure you're in degree mode, you're going to get some decimal approximation. And then if you evaluate root 6 plus root 2 divided by 4, you'll get the same decimal. Let's go on to a second example. Find the exact value of cosine pi over 12. Now again, pi over 12, not on the unit circle. So what we need to do is we need to find two angles that are on the unit circle that add up to pi over 12, or subtract to pi over 12. When we have our angle in radians, sometimes it's harder to see what can add up or subtract to the given angle. Pi over 4 minus pi over 3, that's going to subtract and equal pi over 12, because pi over 4 is 3 pi, or I have this backwards. I think we want to say pi over 4, or pi over 3 minus pi over 4. There we go. So pi over 3 is 4 pi over 12. Pi over 4 is 3 pi over 12, and we see that that is equal to pi over 12. So these two angles would work here. A second way we could do this is to convert to degrees. I think this is probably easier for people to see. So pi over 12, we'll multiply that by 180 over pi. Pi's cancel. 180 over 12, if I divide both of those by 6, we get 30 divided by 2, which is 15 degrees. So if we convert 15 degrees, or use 15 degrees, if we convert or write that as a sum or difference, we could say 45 degrees minus 30 degrees. That may be an easier option for folks. So it doesn't matter which set we use. We can use the set in degrees, we can use the set in radians. I'm going to use radians, but if we use degrees, we would get the same value. So cosine pi over 3 times cosine, actually, why don't I back up a little, just to say what we're doing here. So cosine pi over 12, we are rewriting that as cosine of pi over 3 minus pi over 4. So cosine pi over 3 minus pi over 4, that is going to be equal to cosine of the first times cosine of the second. Now when we have a difference of cosine, the operator changes. So now this is plus, now sine of the first times sine of the second. And then we just evaluate these. So cosine of pi over 3, that's 1/2. Cosine of pi over 4 is root 2 over 2, plus sine of pi over 3 is root 3 over 2. Sine at pi over 4, root 2 over 2. So simplifying root 2 over 4 plus root 6 over 4. So when we add this together, we get root 2 plus root 6 all over 4. And that is going to be equal to cosine of pi over 12. So one thing you may notice as we're going through these is you really need to know the values of the unit circle. We need to be able to evaluate these. You know, there are 4 little evaluations that are happening here, and if you mess up on one of these, you're going to have some problems. You're not going to get the answer correct. So you really got to be able to recall the values from the unit circle. This example says verify that the equation is an identity. We have cosine of x minus 3 pi over 2 equals sine of negative x. Now, a couple things to notice here. One, this right here is a difference for cosine, so we can use the difference formula. Now, one thing we don't want to do, it's very tempting when we see this to write cosine of x minus cosine 3 pi over 2. Kind of like you're distributing the cosine. That is not what we want to do. Okay? We must use the difference identity. And remember, the difference identity for cosine is cosine of the first times cosine of the second. We change the operator for cosine, so instead of minus, this becomes plus, and then we say sine of the first times sine of the second. Okay, so that's what's going to happen on the left-hand side. On the right-hand side, we can tackle this in one of two ways. One way is to note that, well, sine is an odd function. And because it's odd, that means that this, sine of negative x, is equal to negative sine of x. Okay? So this is probably the most obvious way to handle this, and definitely the quickest. So I'll do that for now. Let's finish the proof, and then we'll see the second way we can handle that negative sine x. All right, so back to the left-hand side. We have cosine of x. Nothing we can do there. Cosine of 3 pi over 2. Well, 3 pi over 2 is along the negative y-axis. Cosine is 0 there. Plus sine x times sine at 3 pi over 2 is negative 1. So this all becomes 0. Sine of x times negative 1, well, that's just negative sine x. And then on the right hand, we have negative sine x. And then we got that. Now, suppose you don't remember that sine of negative x is odd. So a second way we could do this, and this is probably, well, this is definitely less obvious to see, but this is a way we could handle that sine of negative x. So sine of negative x, let's turn that into a difference, and I can turn that into a difference of 0 minus x. Well, sine of 0 minus x, to evaluate this, we say sine of the first times cosine of the second. Sine, the operator stays the same, and then we have sine of the second, cosine of the first. So what we'll see here is sine at 0 is, well, that's just 0 times cosine x minus sine x times cosine at 0. Well, cosine at 0 is 1. So what we end up with here is that goes away, and we're just negative sine x times 1, negative sine x. So that is the same thing as we have right here. So maybe a little bit longer and perhaps not as obvious to see. It's definitely quickest to just realize that sine of negative x can convert to negative sine x using the fact that sine is an odd function. Another set of identities for us to look at are called the cofunction identities, and we'll derive these. So suppose we have a right triangle. We have angle theta, x, y, and r. Now, if we know that this angle down here has a measurement of theta, well, that means that this angle has a measurement of 90 degrees minus theta. We could similarly write this as pi over 2 minus theta. And the reason that these facts are true is because, well, the angles in a triangle must add up to 180. We have 90 down here, so what's left is between the other two angles, the sum must be 90 degrees. Well, if we have one angle theta, and suppose, I don't know, that's 40 degrees, that means 90 minus 40 would give us the third angle. Okay, so no matter what theta measures, 90 minus that measurement will give us that third angle. So let's look at what cosine of angle theta is equal to. Well, cosine of theta is the adjacent side over the hypotenuse. And then let's look at what sine of the third angle would be? Well, sine of 90 minus theta. Well, sine is opposite over adjacent, so that is also x over r. Now, because each of these expressions are equal to x over r, they must be equal to each other. So we would say sine of 90 minus theta is equal to cosine of theta. All right, so this is one of the cofunction identities. And there are actually 5 more, and they all relate in a very similar way, and we can find them with this same sort of proof. So cosine of 90 minus theta, that's going to be equal to sine of theta. So these two are cofunction identities. Tangent of 90 minus theta, the cofunction of tangent is cotangent. And then we can reverse things. Cotangent of 90 minus theta is equal to tangent of theta. And then lastly, we would say secant of 90 minus theta is equal to cosecant theta. And then lastly, cosecant theta 90 minus theta is equal to secant theta. So these right here comprise the cofunction identities. Now, I wrote all of these in terms of degrees, but we could also rewrite them in terms of radians. We could, because we know that 90 degrees is equal to pi over 2. So in each of these positions, we could replace the 90 with pi over 2. So we could write the cofunction identities in terms of radians, or in radian measurement. A second way that we can think about these cofunction identities is just using them as with the sum or difference formula. So let's take this first one, this one right here, cosine of 90 minus theta equals sine theta. So cosine of, I'm going to write it in radians this time. So let's prove this. Well, cosine of pi over 2 minus theta, if I write that as a difference, that's going to be cosine pi over 2 times sine theta. Sorry, I had that backwards. It's cosine of the first times cosine of the second. We swap the operator, so this is going to be plus sine of the first, sine of the second. Now, cosine of pi over 2 is 0, so 0 times cosine theta plus sine of pi over 2 is 1, so 1 times sine theta, and then 0 times cosine theta is 0, so this is just 1 times sine theta. We get sine theta equals sine theta. So what that tells us is that, yes, this is in fact an identity. And going back to all of these cofunction identities, we could prove them in a similar way. So the last thing to talk about in this section is the sum and difference formula for tangent. So we've talked about the sum and difference for sine and cosine, but not tangent yet. So what we can do is, well, we know that tangent is just sine over cosine. So we could rewrite tangent of a plus or minus b as sine of a plus or minus b all over cosine a plus or minus b. And then in the numerator, this is just the sum or difference of sine. So we're going to say sine of the first, cosine of the second, keep the sign the same, sine of the second, cosine of the first, divided by cosine is going to be cosine of the first, cosine of the second. We reverse the sign, and then we have sine of the first, sine of the second. So from here, what we're going to do is we're going to divide each term by cosine A, cosine B. Or rather, we're going to multiply the numerator and the denominator by 1 over cosine A, cosine B. Doing so, we're going to get sine A, sine B all over cosine A, cosine B plus or minus, we'll have sine B sine A over cosine A cosine B. So that's what we'd have in the numerator. In the denominator, we're going to have cosine A cosine B all over cosine A cosine B minus plus, and then sine A sine B over cosine A cosine B. Now, this might seem a little contrived, but the reason we can do this, or the reason we do this, is that many of these fractions are going to simplify. So sine A sine B over cosine A cosine B, well, this right here is tangent of A, and then this sine B, this should cancel. I made a slight mistake here. So cosine B, this should be cosine B in here. So let me fix that. Okay, so cosine B over cosine B, well, that just cancels. So that first term we have tangent of A plus or minus. Here we have sine B, again, I wrote that incorrectly. Okay, so sine B cosine A over cosine A cosine B. So we see that the cosine A's will cancel, and then we have sine B over cosine B. Well, that's just tangent of B divided by, well, in the denominator we have cosine A over cosine A, cosine B over cosine B, so that's just 1 minus plus, and here we have sine A over cosine A, so that's tangent A, and then sine B over cosine B, that's tangent of B. So what we end up with is tangent of A plus or minus B. We get this expression, tangent of A plus or minus tangent B, all over 1 minus plus tangent A tangent B. So that is the sum and difference formula for tangent. So why don't we look at an example or two using this. So find the exact value of tangent 17 pi over 12. Now, similar to the sum or difference examples we saw with sine and cosine, 17 pi over 12 is not on the unit circle. So because it's not on the unit circle, we want to write 17 pi over 12 as the sum or difference of two angles that are on the unit circle. Well, if we use 8 pi over 12 plus 9 pi over 12, 8 pi over 12 is just 8 pi over 12, divide the top and bottom by 4, we get 2 pi over 3 plus 9 pi over 12, divide the top and bottom by 3, we get 3 pi over 4. So both of these angles are on the unit circle. Similarly, we could convert 17 pi over 12 to degrees if we would like, and then come up with two angles that sum to that value. So the pi's cancel, divided, cross cancel by 6, we get 30. 30 times 17 is, I think we get 510 divided by 2, so 255, is that right? Yeah, that looks good, 255. So we could take 255 and write that as the sum of two angles that are on the unit circle. The first ones that pop into my head are 210 plus 45. Both of those are on the unit circle, so we could just as easily use these degree angles. All right, I'm going to use the radian measures though. So we're going to say tangent of 17 pi over 12. We can write that as tangent of 2 pi over 3 plus 3 pi over 4. So the identity for the sum of tangent, we take tangent of the first plus tangent of the second divided by 1 minus tangent of the first times tangent of the second. Okay, so from here we just need to evaluate each of these. Now I will say this problem is a little bit more challenging than the sum or difference of sine and cosine. the simplification can get quite messy, but if we're careful, we'll still end up in the right spot. So tangent of 2 pi over 3, that is 2 pi over 3, that's quadrant number 2, so that's going to be negative root 3. Tangent of 3 pi over 4, that's in quadrant 2 also, so negative 1, divided by 1 minus, and then tangent of 2 pi over 3 again is negative root 3 times negative 1. So what we end up with is negative square root 3 minus 1 all over 1, that's going to be negative root 3. Now at this point, we need to rationalize the denominator, and how we do that is by multiplying by the conjugate. So 1 plus root 3 divided by 1 plus root 3. Now the whole reason we multiply by the conjugate is because this will remove the radicals in the denominator. So in the numerator, we need to distribute this out. We get negative square root 3, negative root 3 times root 3 is negative square root 9 minus 1 minus square root 3. And what we'll see in the denominator is we get negative root 3 plus root 3 minus square root 9. So what happens is this negative root 3 and the positive root 3, those cancel. And square root of 9 is just equal to 3. So what we have is, let me do some simplifying up here. This is 3. So in the numerator, we're going to have negative 2 square root 3. So we have 2 negative square root 3's. And then we have negative 3 minus 1. So negative 4. And then in the denominator, we have 1 minus 3. So that is going to simplify to negative 2 square root 3 minus 4 divided by negative 2. And what I'm going to do in the numerator is factor out the negative 2. Divided by negative 2, and then those negative 2's cancel. So what we end up with is square root 3 minus 2. So factor out a negative 2 from the numerator. We're going to get negative 2, root 3 plus 2 divided by negative 2. The negative 2's cancel, and we end up with square root 3 plus 2. So quite a bit of simplification here. And then let's just double check our work. If you take a calculator, make sure you're in radian mode, and you punch this in, you're going to get about 2.73, or rather 3.73. And then if we punch this into the calculator, we also get about 3.73. So if those are the same, then we know that we've done this correctly. I want to do one more example just because these tangent sum or difference questions are a little bit more challenging. So tangent of negative 165. So negative 165, I'm going to write that as, let's see, we can use 45 minus 210 degrees. So we'll say tangent of negative 165 is equal to tangent of 45 minus 210. So tangent of the first minus tangent of the second divided by 1 plus tangent 45 tangent 210. So moving on, tangent 45, that's 1. Tangent of 210, well that is 1 over root 3 or root 3 over 3. That's in the third quadrant. It's positive there, but we use this negative sign. And then 1 plus tangent of 45 is 1, tangent of 210, root 3 over 3. We get 1 minus root 3 over 3 over 1 plus root 3 over 3. Now what we need to do is, there's a couple ways you can simplify this. I'm going to get a single fraction, or rather, I'm going to remove the denominators in these complex fractions. So what I'm going to do is I'm going to multiply the top and bottom by 3 and distribute that through. So what's going to happen is we'll get 1 times 3 is 3, this 3 and this 3 are going to cancel, so 3 minus root 3 all over 3 plus root 3. Now we're back to a similar situation as we had in the last example. We're going to multiply the top and bottom by the conjugate to get rid of the radicals in the denominator. So we're going to come back up here. So in the numerator we'll have 9 minus 3 root 3 minus 3 root 3 plus square root 9 divided by 9 plus 3 root 3 minus 3 root 3 minus square root 9. So some items will cancel in the denominator. This right here is going to equal 3. This right here also going to equal 3. So I have 9 plus 3 in the numerator, that's 12, minus 6 square root 3. In the denominator we have 9 minus 3 is 6. And then from here I'm going to factor out a 6 from the numerator. We get 2 minus square root 3 divided by 6. The 6's cancel and we get 2 minus square root 3. And again, we can check our work using a calculator, and we'll see that we get the same value for tangent of negative 165 and 2 minus square root 3.